Good evening, everyone. So, in today's class, we will be discussing about the electrical machines first assignment. Okay. Now, electrical machines is a very important topic when it comes to electrical engineering because most of the things, if you will study, they will be based on these electrical machines. And also, for understanding the electrical machines, you need to have your circuit theory also well. Okay, because you will find that we will be using the circuit theory to simplify some of the things. Okay, so let us now start with the class. One second. Okay. So here, so this course basically what I will be doing is that I will be discussing the previous year's assignment because we are not allowed to discuss the present week's assignment. You will be given the weekly assignment, and then you will need to complete those assignment to score the daily, what you say, weekly assessment marks. Okay, because those weekly assignments have the marks associated with it, and you will be given the final certificate on the basis of these weekly assessments. That is why we are not allowed to discuss the weekly assignment questions. But however, we are here to clear your doubts. Okay, I am Sakshi Singh from Indian Institute of Technology, Kharagpur. So here I will be discussing what you say, previous year's assignment, which will help you, to क्या कहते हैं, which will help you with the solving of this week's assignment. Okay, so let us see the first. So in our first, what you say, topic, we will be starting with the introduction of electric machines. Okay, so let us start. So our first topic for the week one. Okay, on the basis of which you will be getting your, what you say, this assignment also. Okay, so you will find that the questions which I will be discussing from the last year, it will be helpful to for you to solve this year's question also. Okay, so if you have any doubts, get them cleared, because you will be able to then solve your this week's assignment properly. Okay, so in the first week we will be discussing about the introduction of, okay, transformers. Then what is an ideal transformer? Then we will be seeing the practical transformer. Like in basically in ideal transformer, we will be considering that there are no losses. Okay, but in a practical system, we know there are losses, right? So we will be seeing what those losses are and how to represent them. Okay, so how we will be representing those things? We will be representing it in the equivalent circuit diagram. Okay, so this is equivalent diagram. Okay, so let us start. Okay, so basically for going into the transformer, first of all we will be discussing the very fundamental law, which is the Faraday's law of electromagnetic induction. Okay, so in case you have doubt any time, okay, in any slide, any line you have doubt, so you can, what you say, stop me in between and ask. Okay, so if you type the doubt in the chat box, it will be very difficult for me to go from here and check the chat boxes in between. So it is better to speak in the microphone. Okay, so Faraday's law. So we were discussing Faraday's law of electroinduction. So what it states that the rate of change of magnetic flux induces EMF. Okay. EMF is basically electromotive force or voltage. Okay. We can write it as voltage, electrical voltage. Okay. So what this means that suppose, so you have like how you, so rate of change of magnetic flux, right? So what happens is that you have the magnetic flux, okay, which can change either with respect to time or it can change either with respect to space. So this rate of change, okay, this rate of change can be with respect to time or it can be with respect to space. So let us understand what this with respect to time and with respect to with respect to space means. Okay. So here, so let us take an example of DC machine. Okay, we will be seeing the DC machine, induction machine, and all this in the upcoming assignments. But for now, let us see the DC machine. So what is a DC machine? So in the field, you have the you can either have a permanent magnet or you can have an electromagnet. Okay, so let us suppose that we have some arrangement of magnet which can be the permanent magnet or electromagnetic magnet with the two poles. Now, what are these two poles? One is north and one is south. So we know, right, that we have studied in our what you say school days also that what happens if we keep the two poles of opposite what you say polarity. So what will happen is that there will be there will be magnetic field, okay, which will be going from the north pole to south pole. Okay, so here what will happen is that there will be magnetic field which will be going from north to south pole like this. Okay, so these are magnetic field. Okay, now suppose you have an electric conductor in this magnetic field. Okay, so let us suppose I have the conductor like this. Okay, so this is the magnetic conductor and it will be this terminal will be coming out. So you will see that in a DC machine, this poles, okay, these north and south, basically they are poles. Okay, so these poles will be located in the field. Okay, so poles are located in the what you say, basically it will have in any machine has the two parts, which is the stator winding and rotor winding. Okay, so basically this is located in the stationary winding. Okay, so this is basically stationary, so poles are stationary and your rotor winding is basically this armature winding. And what is this armature winding? It is basically this blue colored wire which you can see. Okay, so there will be multiple sets of blue colored wires which will be arranged in the armature. Okay, so what you have is that you have the like this. So this is the armature part in a machine. Okay, and then you if suppose I'm seeing it from the top, if I'm seeing the machine from the top, so what you will see is, and then there will be this part. Okay, so this basically this part is connected to the what you say this shaft and it will be rotating. Okay, so what you will have is that you will be having some arrangement, like suppose in a hydropower plant you will have the turbine. Matlab hydropower plant, you know, right, that there will be what you said in the dam, you will make the water to flow on the blades, so it will rotate this what you say, this it will rotate this shaft, okay, which will be coupled to a turbine. So suppose this is the turbine which is rotating. It may rotate due to the flow of water, or in the thermal power plants it may rotate due to the flow of steam, okay. तो ये क्या होगा कि रोटेट करेगा, अब ये रोटेट कर रहा है. सो इफ इट इज रोटेटिंग, so this rotating part, okay, so this suppose this is the rotating part. So this rotating part is called as rotor, okay. और ये जो stationary part है, so this stationary part is called as stator, okay. So these iska or bhi detail we will be seeing in the upcoming classes, but I'm just want to give you what this space variation means. I have said this with respect to space, right? So I'm trying to give the example. So ye jo hai, this is stator part. Now in the DC machine, in the rotor part you have this blue windings, okay. So rotor winding you see is this armature winding, okay. So now what happens that, and now what you are doing, you are rotating this. So what you are basically doing is you are rotating this. So suppose we are rotating this in this direction, okay, तो ये rotate कर रहा है. Suppose we are rotating this in this direction. So what will happen that because of the rotation, because magnetic field is stationary, magnetic field जो है वो एक ही जगह पर है, ठीक है. यहाँ पे magnetic field change नहीं हो रहा है. Magnetic field is stationary, and with respect to time, so with respect to space also this magnetic field is stationary, मतलब वो हिल नहीं रहा है. Magnetic field is like एक ही जगह पे जा रहा है ना. ये जो है ये स्ट्रेट लाइंस में जा रहा है. ऐसा तो नहीं कि ये मतलब चेंज हो रहा है, मतलब ये कभी स्ट्रेट लाइन में है कभी जिगजैग लाइन में, ऐसा तो नहीं हो रहा है. वो हर टाइम मतलब स्ट्रेट लाइन में जा रहा है. सो इट बेसिकली मींस व्हाट, कि वो स्टेशनरी है, ठीक है, ये विद रिस्पेक्ट टू स्पेस. और एंड ऑल्सो यू विल सी कि यहाँ पे, क्योंकि ये हम लोग वी आर यूजिंग परमानेंट मैग्नेट और इलेक्ट्रोमैग्नेट इन द फील्ड, सो दिस इज लोकेटेड इन द फील्ड और द स्टेटर पार्ट, ठीक है. So यहाँ पे क्या करते हैं, we will be having some arrangement due to which this magnetic flux will flow. So what happens is कि because this is DC, what you say, we will be giving it a DC field, which you don't get too worried, okay. We will be seeing all this in the upcoming classes, okay. But just think कि ये जैसे permanent magnet है, ठीक है. तो permanent magnet में क्या होगा कि ये जो flux जो है तो constant रहेगा ना, with respect to time also. तो with respect to time also this flux is constant, okay. तो ये फ्लक्स अपने आप में चेंज नहीं हो रहा है, ना तो विथ रिस्पेक्ट टू टाइम चेंज हो रहा है, ना तो विथ रिस्पेक्ट टू स्पेस चेंज हो रहा है. तो अब हम लोग क्या कर रहे हैं, अब हम लोग ये जो कॉइल जो है वी आर रोटेटिंग दिस कॉइल. सो व्हेन वी रोटेट दिस कॉइल व्हाट विल हैपन इज, ये कॉइल को विथ रिस्पेक्ट टू दिस कॉइल, कॉइल को फ्लक्स जो है चेंज होता हुआ दिखेगा, ठीक है. फ्लक्स जो है वो अपने आप स्टेशनरी है. like suppose someone is standing on the platform, मतलब ट्रेन है, someone is sitting in the train, और एक someone is standing on the platform. तो yellow lines is someone who is standing in the platform, वो अपने आप में stationary है, ठीक है. लेकिन suppose अगर कोई ट्रेन पे बैठा है, जैसे ब्लू ये जो ब्लू वाला जो है आर्मेचर जो वाइंडिंग जो है, ये suppose करो someone is sitting on the train, तो वो क्या हो रहा है, it is changing विथ रिस्पेक्ट टू स्पेस. ट्रेन तो मूव कर रहा है, तो विथ रिस्पेक्ट ये रोटेट कर रहा है, जैसे यहाँ पे जो रोटर जो है रोटेट कर रहा है. तो ये आर्मेचर वाइंडिंग जो ब्लू वाइंडिंग जो है इट इज रोटेटिंग, ओके, इट इज रोटेटिंग इन द डायरेक्शन ऑफ एरो. तो क्या होगा यहाँ पे, ये पर्टिकुलर वाइंडिंग के लिए देयर विल बी द चेंज ऑफ फ्लक्स. वो चेंज ऑफ फ्लक्स कैसा है, विथ रिस्पेक्ट टू स्पेस. तो क्योंकि यहाँ पे चेंज ऑफ फ्लक्स विथ रिस्पेक्ट टू स्पेस है, तो इसीलिए इसके अक्रॉस में ईएमएफ इंड्यूस होगा, ये वोल्टेज जो है इंड्यूस होगा, ठीक है. तो ये एक तरीका है जिससे कि हम लोग मैग्नेटिक फील्ड we can what you generate EMF. तो the Faraday basically what he did was he actually made this DC generator, okay. तो he made this DC generator which he called as dynamo, okay. तो उसने यही प्रिंसिपल से उसने देखा कि अच्छा, अगर वो कॉइल को जब वो चेंज करता है, बेसिकली इफ ही चेंजेस द कॉइल, ओके, इफ ही चेंजेस द कॉइल इन द मैग्नेटिक फील्ड, तो वो देख रहा था कि उसपे उसके क्रॉस ईएमएफ इंड्यूस हुआ, ठीक है. तो ही अंडरस्टूड कि अच्छा, इफ आई चेंज, इफ देयर इज अ चेंज रेट ऑफ चेंज ऑफ मैग्नेटिक फ्लक्स, तो उसमें ईएमएफ इंड्यूस होगा. लेकिन तब उसको ये विथ रिस्पेक्ट टू टाइम के बारे में पता नहीं था, उसको ये विथ रिस्पेक्ट टू स्पेस के बारे में पता था, ठीक है. तो उसने क्या किया, उसने अपने हाथ से वो कॉइल को घुमाया और उसने देखा कि अच्छा यहाँ पे जब वो दो दो मैग्नेट के बीच में जब वो ऐसे हाथ से कॉइल घुमा रहा है तो उसमें ईएमएफ प्रोड्यूस हुआ, ठीक है। तो उसको ये विद रिस्पेक्ट टू स्पेस के बारे में पता था, ठीक है। तो उसका जो भी कॉन्सेप्ट था उस समय विद रिस्पेक्ट टू स्पेस था, तो उसने रेट ऑफ चेंज बोला मैग्नेटिक फ्लक्स इंड्यूसेस, पर उस समय वो रेट ऑफ स्पेस चेंज विद रिस्पेक्ट टू स्पेस था, ठीक है। अब ये विद रिस्पेक्ट टू टाइम का कॉन्सेप्ट जो है वो हम लोग देखेंगे इसके साथ, बेसिकली वी विल बी सीइंग इट विद योर ट्रांसफॉर्मर, ठीक है। तो अब ये विद रिस्पेक्ट टू टाइम क्या होता है वी विल सी। सो ओके, सो बिफोर गोइंग हियर लेट अस सी दिस थिंग्स आल्सो, ठीक है। अब मैंने ये बात किया कि सो देयर विल, सो व्हाट हैपेंस इज फर्स्ट ऑफ ऑल one thing is that we have seen Faraday's law, right? तो फराडे ने क्या बताया कि ईएमएफ इंड्यूस होगा। हाँ, यस। Okay, sorry. I'll speak. Actually, like I have taken some classes previously, so some people insist on taking in Hindi also. I'll speak in English, okay? And if suppose someone is having issue with the like, if sometimes someone wants me to speak in Hindi also, they can speak. I am comfortable in both the languages, okay? So let me know anything, okay? Okay then. So this is basically, sure, rate of change of flux. Now, the second thing is ki I said, right, ki if I keep the magnets like this, then there will be magnetic field. So someone would have discovered this, right? So it was discovered by Oersted, okay? He found that he basically what he did was he traced the magnetic field by keeping what he did. He kept the magnet, what you say, two magnets like this. Okay, not like, actually he did not keep the two magnets. Basically, on the same magnet, because you know, right, on the same magnet also itself we have north and south polarity, right? So he had a magnet like this, oystered, okay. So what he did was he basically traced ki acha, so this field lines will go from north to south like this, okay. So he traced it like this, okay, that he traced each and every lines by what how he did it, he put compass in between, okay. He put compass and saw, okay, how is the what field lines going. So he put compasses in between, and then he saw ki okay, magnetic field is basically traveling from north to south, okay. So like that he traced it. So this basically the what you say magnetic, the concept of magnetic flux, okay, it was what you say discovered by Oersted, okay. Now, after that, Faraday did his thing. Okay, if there is magnetic flux already there, and if I change it in what you say, if I produce some rate of change in the flux, then there will be EMF induced. Now, there are some rules, okay, that there are some rules between the flow of current and how the EM flux lines are produced, okay. So that we can give by some of the methods. So this is basically right hand thumb rule, okay. So this is right hand thumb rule in a conductor. You can see that I have two images, right? And this one is right hand thumb rule in a solenoid or coil. Okay. So what happens? Suppose you have a conductor, straight conductor like this. Okay. And if you pass, and there is a current flowing in this conductor. Okay. So if suppose there is a current flowing in this conductor, in this straight conductor, so as per this right hand thumb rule, if you put your right hand like this, okay, right hand thumb like this, like sorry, um, highlighter, yes. So if you put your right hand like this, okay, your thumb is outwards like the logo of thumbs up, okay, and you curl your all the four fingers inside in this way, okay. So what you can do, you have to put the thumb in the direction of current. So in this case you can see that the current is flowing upwards, okay. So this, suppose this current is flowing upwards, so current flow is upwards. Okay, current is flowing upward. So you put the thumb in the direction of current, matlab kaun se in which direction the current is flowing. Okay, so the curl of the fingers, so the curl of fingers like this will show you the direction of magnetic field. So you can see that the magnetic field is like this, okay, in the direction of the other four fingers. Similar, in the alternate way, if suppose you have coil like this, okay, so basically you have the coil like this, so this is like this, and I have coil like this. Now in this coil there is a flow of current, right? Suppose the current is flowing like this, okay? So what you will do, you will again curl your four fingers in the direction of the current, okay? So if you curl your this other four fingers as shown here in the direction of current, okay? So because this is the direction of the flow of current in the coil, so we are putting our aligning our other four fingers along this. So what will your thumb direction give? It will give the direction of the magnetic field. Okay, so the magnetic field is starting from here. So basically this will be like the North Pole. Okay, and the magnetic field will go like this and it will come back here. So this point will be South Pole. So it will basically give you the direction of North Pole, okay, of the magnetic field. So these are the two rules, okay. So we will be using these two rules for the transformer. That is why I discussed this, okay. Now let us go to the transformer, okay, which is the which you will see the assignment questions and the basic principles of transformer in this week, okay. So is there any doubt till now? Is there any doubt, like if किसी को कुछ doubt है, like what is this with respect to space means? With respect to time we will come, okay. Now I'll come to the transformer, then I'll discuss this, okay. But here or in this two definitions, is there any doubt? Okay, so let us go to the transformer, okay. So you see this transformer, it is a static device, okay. So what does this static term means? That there is no movement, okay, no rotation slash no movement, right? You will see that the other electrical machines like motor, generator, they are not static device, okay, they are dynamic device, but this transformer is a static device. Now you can see that so basically the those devices are, so you see, as per the proper definition of electrical machine, transformer is not an electrical machine, okay. What does actually electrical machine, okay, are the devices which are capable of continuous electromechanical convergence, okay. Means there is some electrical part and there is some mechanical part, okay. Mechanical part means what? Mechanical movement. जैसे कि in the previous DC machine case, we saw that there is the movement, right? There is a rotation. So basically there is an electromechanical conversion. मतलब if suppose in the case of generator, what we do that we give some rotation, we get electrical energy. Similarly, in the case of the motor, you will see that if we pass the electric current in this conductor, so it will start to rotate, okay. So that is, so basically there is what, there is an electromechanical conversion from electrical energy to mechanical energy, and from mechanical energy जो कि here we are providing in the form of rotation, right? यहाँ पे like in the turbines of the what you say, turbines, thermal power plant or hydropower plant, there is a rotation provided which gives us the electrical energy. So there is an electromechanical conversion, means electrical energy to mechanical energy and mechanical energy back to electrical energy, okay. So those machines are called as electrical machines as per the proper definition. But in the form of, in the transformer, there is no electromechanical conversion, okay. There is only an interchange of voltage levels or current levels, okay, in the transformer. So as per the proper definition, it is not an electromechanical machine or electrical machine. Okay. So let us see how the transformer basically works. Okay. So let us see the concept of working of the transformer. So here, as you can see, that we suppose we are giving a voltage source, which is shown here. This voltage source is applied across one winding of the transformer. Okay. Now in this winding, we will discuss this dot convention. Okay. So for now, just think that I have put a dot. Okay. So I have put one dot here. So what will happen is that you are giving the current. So how the current is flowing? So the current is flowing, okay, in this way. So this is the flow of the current. Okay. Or so this is the flow of the current. Let us see. So this is the flow of the current. Okay. Now we have seen the right hand thumb rule. So can someone tell me in which direction the magnetic flux will be for this case? Will it be this magnetic flux will be upward like this flux, or will it be downward like this? So you have like this. So please curl your four fingers in this direction and see where your thumb points. आप लोग क्या करो कि आप लोग जो अपने other four fingers हैं, please orient them in this direction and let me know where your thumb points in the right hand. Okay, whether it points downwards or whether it points upwards. We have discussed this. Okay, so we have discussed this. So please tell me the direction of your thumb in this case, so that I can so we can tell that where the magnetic flux is. Okay, in which direction, upwards or downwards. So can someone tell me in upward direction? Please check properly. Huh? Please check properly. Up, downward direction. Okay, it will be in downward direction. Okay, it will not be in upward direction. Why? So it is like this. Okay, it will not, it is not in this direction. Okay, it is in downward direction. See, your fingers are curled in which direction? You have to curl them like this. Okay, so if you do this for your right hand, because so what you will see your thumb will come downward. Okay, so the magnetic flux lines are going in the downward direction. Okay, so that is the case. So magnetic flux are going downward. So up, so what will happen? So this is the flow of magnetic flux. Okay, so this is how the magnetic flux is flowing. Now we will see, we will discuss something called as Lenz's law. So what is this Lenz's law? Okay. So according to Lenz's law, the direction of induced EMF is such that if it is allowed to cause a current, okay, I then the current so produced oppose the cause. Okay. So this is a very important law. Okay, very important. Like in case of all the machines, we will discuss that everything depends on this Lenz's law. Basically, Lenz's law is nothing but your law of conservation of energy. Okay, so it basically, so basically in other language, Lenz's law is nothing but law of conservation of energy. Okay, so what does it mean? You will see that this law will be applicable in all the machines, okay, everywhere. Not only transformer, you will see it will be applicable in DC machine, it will be applicable in induction machine, okay. So what is this law of conservation of energy? We have studied this in our 7th standard, okay. So can someone tell me what is the law of conservation of energy? Very basic law. On this law only the whole universe operates, okay. So I hope you have heard this. Energy can neither be created. Yes, correct, correct. Okay. So Lenz's law is also exactly the same. Okay. The Lenz's law is exactly the same. So what does this Lenz's law say? Lenz's law in this Lenz's law, what is saying is ki because there is a magnetic flux, right? Because you have provided it a voltage source. This voltage source caused the current to flow like this, and because of this current, there is a magnetic flux which is downwards. Okay. Now this magnetic flux is like this, right? Now there will be some EMF induced in this winding. Okay. Now we have to find out how this EMF is induced. Okay. In which direction the EMF is induced. So Lenz's law is what it is saying ki the EMF in the secondary winding will be induced in such a way that if the current is allowed to flow in the secondary winding for that EMF induced, then it will oppose the cause. So what was the cause? The cause for the EMF induced in the secondary winding was this flux. Okay, this flux was the cause. Now so the current should oppose the cause. So whatever current will flow in the secondary winding due to the EMF induced, it should oppose this flux. Okay. So if suppose this flux is upwards for the secondary winding due to the primary winding. The primary winding ki wajah se flux was going like this, like this. Okay. So let me use this. So, hmm, एक minute. Okay. So I was saying ki due to this, in the primary winding, we have given a voltage source, and due to the voltage source, the current was flowing in this way. Due to this flow of current, there was the flux which was produced. Okay, so this flux which is produced, we have found out from the right hand thumb rule that it is in this direction. Okay, it is in this direction. So magnetic flux is in this direction. So so as per the Lenz's law, in the secondary winding, we have to find out ki EMF will be induced in which direction. The EMF positive terminal will be upwards or positive terminal will be downwards. So we have to find this out, right? So how we will find this out? So we will start with the cause. So what will be the cause of the EMF induced in the secondary winding? It will be this flux. Okay, this flux which is flowing in this path. So yeah, जो भी current will whatever current will flow in the secondary winding, that should induce the flux in the opposite direction. So it means that current will so in which direction the flux will be induced due to the secondary winding voltage, it will be in the downward direction as per the Lenz's law. ठीक है. So suppose the flux is in downward direction because it has to oppose this upward direction flux. Okay, so let us write. Okay, so this flux primary is the cause. Okay, and this flux secondary is the effect. So as per the Lenz's law, the effect should oppose the cause, क्योंकि law there is a conservation of energy. ऐसा तो नहीं है ना कि यहाँ पे भी the flux which will be produced here will again be in the same direction. So it will basically means you are increasing the energy. Okay, that is not happening. So what is happening is we are basically so there is only the change of energy form. So it is something like कि so it is not like the energy will keep on increasing, right? So that is why this effect should oppose the cause. Like suppose you are moving your car. So the car you are moving, the car what so the what will be opposing the effect of what you say motion of car? It will be what? It will be friction, right? So there is a friction when the car is moving, because that is friction is the effect and it is opposing the cause. Similarly here also this secondary flux, secondary winding flux which will be produced should oppose the primary flux, which is the main flux. Okay, so what will happen? So if the flux in this form is in this what you say in the secondary winding has to be in the downward direction. So what should be the direction of current? So you put your what you say this thumb in the downward direction. Okay. So if you put your thumb in the downward direction, okay, in the direction of the secondary flux. So, 1 second. So you will find कि the current as per this right hand thumb rule which we have discussed, कि if the flux is in downward direction means what? So in which direction will be the current? You can use the right hand thumb rule and you will find the current will be in this direction. Okay, so if you put your thumb downwards in the direction of this phi secondary, okay, right hand thumb, so you will find that your fingers will curl in what way? It will they will curl in the clockwise direction. Okay, so in this way the what you say your current will flow. So current is flowing like this. So if your current is flowing like this means what? If you connect a load, so it will be like you have connected your EMF like this, because if you connect the EMF like this, the current will flow like this, is it not? So current will flow from where? Current will flow from positive potential to negative potential, right? So the direction of EMF will be with the plus sign upwards. Okay, so this is what the Lenz's law is saying. Lenz's law is saying कि direction of induced EMF which is E2 is such that if a current is allowed to flow, देखो ये blue वाला जो है the blue arrows show the current which is allowed to flow. ठीक है, so the blue arrow is the current which is allowed to flow due to this EMF, right? So ये जो current जो flow कर रहा है, it will it then the so it is such that it will oppose the cause. So what was the cause? The cause was this phi primary. So the effect which is this phi secondary will oppose the cause which is phi primary. ठीक है? So this is the fundamental of the transformer. If you understand this, you can do all the questions. Okay, this you have to understand. Okay, if you can understand this, then your most of the things you have understood. Okay, so is there any doubt? Whichever I have discussed, whatever I have discussed, is there any doubt? If you would like, I can repeat also, because this slide is very important. Okay, so please let me know if there is any doubt in this slide. Okay, this slide is very, very important. If you would like, I can discuss it again. Someone is saying something. Okay, Gayatri, do you have any doubt? If you have any doubt, then I can discuss this slide again, because this slide is very important. Okay, so questions are like questions are not very difficult for this week. They are very simple questions, but this concept is very important, because okay, and this understanding the Lenz's law for each machine is very important. Okay, this law is like the main law which will give you the fundamental of all machines. Okay, so in case if you have doubt, you can always see the recorded lectures. Okay, we will be sharing the recorded lectures with you, so you can follow. If you're not able to understand right now, then you can see it one more time. Okay, after the class is done, then you can ask me again in the next class, or maybe you can ask me in that the link where I will be uploading. In that down there are the comment section, so there you can ask. I'll clear it. Okay, so see, you can see, go through the recording. Okay, so this is what. Now we have I have discussed something called, there is a rate of change of magnetic flux, which may be with respect to space, as in the case of DC machine, induction machine, or it may be with respect to time. Okay. Now in the transformer, you can see that there is no change with respect to space, right? It's not like a transformer is rotating. Transformer is a stationary device. So how will this EMF will induce? Okay, so there has to be a rate of change of flux. So you will see that the rate of change of flux will be in with respect to time. Okay, so how is the flux? So this is how the flux is. So you will see that it is, so that is why when we connect a voltage source, it always has to be an AC voltage source, because in AC there is a variation with respect to time. Okay, so that is why this is the flux phi m. Okay, so if suppose this is phi m, this is the peak, basically phi m. Okay, now what is phi? Yes, tell me, ask me if there is any doubt. Okay, okay, phi is phi m sine omega t. Okay, so it is like this. Now as per Faraday's law, what is E? E is uh, basically E is rate of change of flux linkage. Okay, lambda is flux linkage. Okay, positive and negative I wrote in here, this plus minus, because this plus minus you can decide as per this discussion. Okay, this can be plus or it can be an opposite way, depending on how you have what you say. Depends on the sense of winding, because see, the winding can be like this in the primary. Suppose this is the primary winding right now, right? The winding can be like this, or the winding can be in this way also, right? So this is called as different senses of winding. Matlab how you are winding it. You can wind it in this way, like in this example, or you can wind it in this way. Okay. So depending on the sense of winding, you can find out ki how will be the EMF induced. If I so you can see that. Okay. If I reverse this sense of winding, you can try this assignment in your after the class. If you keep this one, you can try to keep this sense of winding, and you keep this sense of winding same, then you will find ki EMF will be induced in the opposite way. Okay, the plus will come down. So it is not necessary ki the plus sign of E2 will always come up or it will always come down. Okay, it depends on the sense of winding. Do you understand, right, that these two are in different way? See, so if you allow the current to flow, so in this way the flux will be downwards, as per the, and in this one the flux will be upwards. Okay, so depending on this, and if you do not change this winding, you will find ki E2 polarity will be plus in this, like in this sense of winding, and in the other case the plus will come down. You can try this at your home. Okay, now we were talking here the flux linkage, right? So what is this lambda? Lambda is basically number of turns into flux. Okay, so this is number of turns into the flux. Okay, now what will be E1? E1 will be nothing but your N d phi by dt. If we take n as constant, okay. Now we have seen what is phi. Phi is phi m sine omega t. Okay. So what will happen to this n d by or dt of phi m sine omega t? So this will become what? This will become n phi m. And you know what is the derivation of this sine omega t? It will be omega cos omega t. Okay. So this is nothing but n phi m omega sine of omega t plus 90. Okay. Now if I write this phi m and this omega s 2 pi f. Okay. Sine omega t plus 90. So this is E1. Okay. Now if I have to tell you the RMS value of this E1, so what is will be the RMS value? We know for a sinusoidal signal, if for a sinusoidal signal, okay, like this, A sine omega t, if you do this root mean square, okay, you can derive this. You can do it like this, that in a one time period, if you do this, you will get A by root 2. Okay. So here the RMS value will be from that same this A by root 2. I have just taken this n phi m 2 pi f, which is the A in this case. So A by root 2. Okay. So your E1, which is the RMS value, will become, okay. So it will become like this. Now, in this case of this, what you say we have, so this was suppose here like this. Okay. And you suppose there are n1 number of terms. And here if we have n2 number of turns. Okay. And this is the phi m. Basically phi, which is phi m sine omega t. Now E1 is what? N1 d phi by dt. And E2 is what? Is N2 d phi by dt. So from the previous discussion here, so what we will get the RMS value of this, suppose this E1, small E1, we will get RMS we are indicating as capital letters, okay? And the, what you say, instantaneous voltage with this with respect to time, we denote it by small letters, okay? So what will be E1? So E1 is E2, this is RMS of E1, and this is RMS of E2, okay? So if I take this E1 by E2, you will find it becomes proportional to N1 by N2. Okay. So this is one major equation. Okay, we will be seeing this. Okay. So this is E1 by E2 is equal to nothing but ratio of the turns. Okay. So this is called as turn ratio. Okay. Now we will do the, Okay. So this root 2 pi, you will see if you do this root 2 into pi, you will see it will become 4.44 F into phi m. So in the many textbooks, you will see that this root 2 pi is written as 4.44. Okay, this ratio. Hmm. So this will come out to be like this. Now we will see the MMF balance. Okay. Of ideal transformer. Now in ideal transformer, there are some assumptions. Okay. So what are the assumptions of an ideal transformer? So these are the assumptions. Okay. So first is that there are no losses. Okay. Second is that there is a magnetic permeability of the, because see, these are the coils, right? Now coils are wound on some iron core, so we are assuming that this iron core, this is the iron core. Okay, this thing. So this is what I meant by iron core. So this one here I am telling as iron core. Okay. So this iron core, the permeability of iron core is infinite. Okay. So this is what I'm saying. So when this permeability is infinite, so what will happen is that, so you will see that flux is what? Flux is nothing but MMF by reluctance. Okay. Like in the case of the, what you say, you would have, maybe if you would have gone in the previous class taken by the other TA, then he would have discussed the similarity between the this, what you say, flux, what you say, electrical system and magnetic system, right? Magnetic circuits. So you would see that he would have discussed it like this, that this flux is MMF by reluctance, which is similar to current is voltage by resistance. Okay. Voltage or EMF. So this is EMF by resistance. Okay, this is for magnetic circuits. This is for electrical circuits. Okay. Now MMF by reluctance, then you will see that reluctance is given by L by nu A. So what will happen to flux? Flux will become, so if suppose your nu is infinite, so what will happen is, okay, so this is, sorry, this is the current. So you will see that basically this MMF is Ni. Okay. Ni by reluctance. So if I rearrange this, so the current required for setting up this magnetic flux, right? There will be some current required for setting up this phi m in, because we have connected this input AC voltage source which was giving some this I naught. Okay, I naught is the low load current which is required for setting up this magnetic flux phi primary. Okay, so yeah, in this case the I naught which will be required. Okay, in this case, in the case of ideal transformer with nu is equal to infinity, because nu is infinity, so the I naught required will be 0. Because nu is so much that it will, there will be always a magnetic flux, because this is an ideal transformer, right? For something ideal, you do not need to do any work, right? So that is because this is an ideal transformer, nu is infinity. So the no load current or the work required for setting up the magnetic flux is 0. Okay, so this is the assumptions of the, what you say, your ideal transformer. Now we will see the MMF balance here. Okay, what is the MMF balance? So MMF balance of ideal transformer. So here I discussed basically the ideal transformer assumptions. Okay, this is not, this is just the ideal transformer. Okay, now we will discuss the MMF balance of ideal transformer. Now for an ideal transformer, what will happen is that this is the transformer. Okay, now suppose this is the current which is flowing. Similarly, uh, sorry, this is the current which is flowing here, I2, N1, N2. Now we have seen one very important thing, right? What we have seen that this phi secondary is opposing the phi primary. Basically, the MMF which is produced by the primary, what you say, this should balance out the MMF of secondary winding. Okay, so basically this is what I mean by MMF balance. So basically what it is, what? So N1 I1, okay, because phi primary plus phi secondary, they are in opposite direction, it should be 0. And now what is phi primary? N1 I1 by reluctance plus N2 I2 by reluctance is 0. Okay, so this N1 I1 plus N2 I2 is 0. Okay, because there is no external MMF required, so there is no I0 in this term. Okay, so I0 is 0 for the ideal transformer, and we have discussed that why I0 comes out to be 0, right? So this is the case. Now what will happen? You will find that I1 will become minus N2 by N1 into I2. Okay, so this is the thing. Okay, so this is the MMF balance for ideal transformer. Now we will discuss the practical transformer. Okay, so now let us discuss the practical transformer. Now you will see that for a practical transformer, first of all, what we have taken the assumptions, there are no losses and nu is infinite. Now these assumptions are not valid. Okay, so what we have is that there are some losses. Okay, and also the nu is not infinite. So this nu is not infinite, and there are losses. Okay, so these are the two things. Now for this so all this discussion which I did from the very beginning, and you will find in the textbooks like this is all ideal transformer. Okay, now for an ideal transformer, if I have to draw the phasor diagrams, so let me complete it. So if I have, so this is phi m sine omega t. Now what about E1 and E2? E1 and E2 we have seen is nothing but N1, suppose in this case it is N1 root 2 pi f N1 phi m cos omega t and root 2 pi f N2 phi m cos omega t. So this is what? Cos. So this, if phi is sinusoid, so that EMFs are cos waveforms. Okay, so cos means what? Cos means this. So okay, so this is suppose E1 and this is suppose E2. This is E2. Okay, so if I have to draw a phasor diagram for this, so what will be the phasor diagram? So if phi is on this axis, so what will happen to E1 and E2? Because phi is sine, and E1 and E2 are cos. So the phasor diagram E1, E2 will be leading the phi by 90 degrees. Okay. Similarly, E1 will also lead by 90 degrees. Oh, sorry. So E1 will also lead by 90 degrees. And you can see that E1 magnitude is more than E2. That is why E1 arrow also I have drawn upwards from E2. Okay, so this is the phasor diagram for an ideal transformer. Now, when we come to the practical transformer, okay, so what will be the phasor diagram? So let us now see. So here, the first thing is that the phi thing is same still. Phi is on this axis, and E1 and E2 are leading the phi by 90 degree as per the Faraday's law. Okay, so this is suppose E1. So at any time you have doubt, please tell me, okay? I'll stop it and I'll discuss your doubt. Okay, this is mainly for your doubt clearing. Okay, so that you do not have any doubt. And this is E2. Okay, so it is like this. Now for a practical transformer, till here it is okay, but you will see that we will have something called as I0, because since nu is not equal to infinite, so we have seen that for an ideal transformer, the I naught was zero, right? So it was the, what you say, the current which was required for setting up the magnetic flux, the main flux. Okay. Now in this case, the I naught is not zero. So what is the direction of I naught? I naught is like this. Okay. So I naught is here. Okay. And this I naught has two components. One which is along this flux phi. So this we called as I phi, which is I naught of, suppose this is the angle phi 0. So this will become I naught sine phi 0. This is the magnetizing component of no load current. I0 is no load current. Okay. And then we have the IC, which is this I0 cos phi 0, which is, so I'll write this. So this is your core loss component. Okay. Because see, when you are giving some current to set up the magnetic field, it is not necessary that the whole current will be utilized for setting up the magnetic field, right? This I, it's not like this I0 will be only I0 sine phi 0. There will be some losses because this is a practical transformer, so it is having some lossy elements in the iron core. So that is why some of the current, I no load current which you're supplying will be utilized in meeting those core losses, basically your hysteresis losses and all the eddy current losses and all that. Okay, so that is why it is having two components now, because there are losses present in the system. Now what will happen to the mmf balance for a practical transformer? So you will see it will become like this. Okay, N1 I1. In the previous case, we have seen that N1 I1 minus N2 I2 plus N2 I2 was 0. Now in this case, it will be like this. Okay, I1. Okay, so you will find that it will come out to be, okay. So this will be the case for a practical transformer. Okay. Now we will see the circuit diagram of the transformer. Okay. So first of all, what we have now, so we have now the core losses, right? You can see that this no load current are having two components. One is this magnetizing component and one is the core loss component. Okay, and you can see that this basically this I1 is the summation of this I2 plus I0. Okay, so let us now first what you say, include the copper losses. So copper losses means what? Because because for the winding, for the coil which you are putting it on the transformer core, it will have some, what you say, copper losses, and also it will have some leakage. Okay, so for what representing this copper losses, we are putting the R1, and for representing the leakage, we'll be putting JX1. Okay, and then similarly on the secondary winding, also you will have R2 Jx2. Okay. So here you have I1. This is V1. This is V2. And this is I2. Okay. Now here this is E1 and this is E2. Okay. And this ratio is N1 is to N2. Okay. So we have assumed that the phi and basically, so I have not discussed about the BH curve, right? So we have a BH curve. So we are assuming that this uh, BH from the BH curve, we are taking the linear part. Okay. So for the linear part of BH curve, you will see BH curve basically gives us how much of the hysteresis loss is present in the any what you say magnetic material. So in the generally for a transformer, we use the iron core what you say core of the transformer. So for the iron core transformer, we operate on the linear region. Now you will see for a linear region, the B will be proportional to H. Similarly, you will see that the phi will be proportional to I. Okay, so we are operating in this linear region. So that is the one thing which I wanted to tell. Now, this is the transformer, but we also have to include what? We also have to include the what you say this no load current, because we have not at all considered no load current anywhere in this diagram, right? We have only considered what you say, we have only represented the coils which are basically put. So these coil and this coil we have represented, but till now we have not represented this iron core losses, right, and the magnetizing component. So we have to do all that. So now first let us do that quickly so that we can start discussing the questions also. So okay, so let us now do this. Okay, now you will see that we have drawn this current, right? But now this I1 is having two component. One is this I0 and the other is N2 by N1 I2. Okay, so how we will represent it? So we will represent it like this: R1 JX1. Here we have I1 and we have R2 JX2, and this is what? This is I2. Now, if I refer this current to the primary, okay, if I refer this current to the primary, so what this will have, what it will become? So we have seen that basically we have seen this MMF balance, right, of the of an ideal transformer. In case we take ideal transformer, then you will see that what it will become. So if I talk about the magnitude, okay, so what will happen to the magnitude? It will become what? So it will become N1 I1 basic is equal to N2 I2. So if suppose I am talking that what will be the referred what you say component of this current I2 to the primary. So let us write it as I2 dash. Okay. So what will I2 dash become? It will be N2 by N1 I2. Now I'm talking this about the magnitude. Okay, you know that this will come with the opposite sign. So opposite sign means nothing but the direction of current. So in this direction the current is going outside, and in this direction the current is coming inside. Okay, inside. So it is entering this what you say winding, and here it is leaving the winding. Okay, so that is why that minus sign will come. Now this is I2 dash. Okay, but I1 is what? I1 for an ideal practical transformer is what? It is basically this N2 by N1 I2, which I have written N2 by N1 I2, I2 dash. Okay, plus I0. So this is that I0. Okay. Now this I0 also has two components we have seen earlier. So that is why, so I0, so we can see that there is some component which is what you say 90 degree to the what you say E1, right? So you can see here that we have E1 here, right? So there is one component which is 90 degree to E1. So that is why we have represented it by a inductor. Okay. So to draw like this, you will see it is something like this. Okay. So here we have E1. So here we have E1. Now we have seen that this I0 has two parts earlier, right? So there was one part of I0. So this I0 one, so even you see even is here. There is one part which is I5, which is 90 degree to this E1. See, there is a 90 degree between this I5 and E1. Okay. So to represent this 90 degree, we have introduced this inductor. Okay. So this inductor is JX5, and that is why, because this current was what? This current was I5, which was magnetizing current. That is why this inductor is also called as magnetizing inductor. Okay. And to represent the in phase component of this I0, because this I0, the component which is in phase with this E1, which is this IC, it represents the core loss. And also because it is a core loss, so to represent the loss like this, we have introduced some resistance, because the real power loss happens across the resistance, and also the resistance causes this E1 and IC to be in phase. Okay. So that is why we have represented this resistance, and we will be writing it as RC. So this is what? This is core loss resistance. Okay. So that is why you have two components. So this is IC. Okay. Now this is the equivalent circuit. But this equivalent circuit, we will now refer it to the primary. Okay. So we will now refer this equivalent circuit to the primary. Okay. So how we will refer it? So let us now do like this. So this is E2, right? This is E2, and this here was V2. Now if I write the equation here, so what is the equation on this secondary winding side? This is the secondary winding side. Okay. So secondary winding side, the equation is E2 is equal to V2 plus I2 R2 plus J I2 x2. Okay. And remember, we have something called A is equal to N1 by N2. Okay. Now what I'll do, I'll multiply by A on both sides of the equation. So first of all, this equation E2 is equal to V2 plus I2 R2 plus J I2 x2, I have written by using the KVL in this, right? So I have written it using the KVL. You can use the KVL and write it. Okay. Now what I'll do, I'll multiply LHS and RHS by A. So what this will become? A E2 is equal to A V2 plus A I2 R2 plus J A I2 X2. Now we have seen something, right? Now what we have seen? We have seen that this AE2, we have seen that E1 by E2 is nothing but N1 by N2, which is A. So what happens to E1? E1 is AE2. Okay. And another thing is that, so what I'll do, what you say, write this as AE2 as E1. Okay, so this will become E1, and this AV2 I'm writing it as V2 dash. It basically means what? The V2, if I refer it to the primary, it will become V2 dash. Okay. So this is V2 dash. See, I have not written V2 dash as V1. So why I have not written is at V1, I'll tell you. Okay. So you can see that V1 is here. I have not written the what you say this AV2 as V1 because there is a difference of R1X1 and R2X2 between V1 and V2. Okay, so to consider that, I have not written it as V1. I'm instead writing it as V2 dash. Okay, now this AI2 R2 I can write like this: I2 by A square R2 plus J I2 by A square x2. Now, what is this? So you can see that I2, basically this I2 dash. I2 dash is what? I2 dash is N2 by N1 into I2, and this is what? 1 by A I2. So to write I2 dash here instead of I2, I have written it as I2 by A. Okay, so I2 by A. So this becomes what? I2 dash A square R2 plus j I2 dash A square x2. Okay, so I will write now here the what is circuit diagram which is referred to the primary. Okay, so till here, because these components are anyway there in the primary, so there is no change in these components. Okay, there is no change in these components. Now I have referred here these. So I have referred what? V2 dash. Okay. And you see here we had E1. So here still we have E1. Okay. This is R1 JX1 RCJX0. Now you see after this RCJX0 across this shunt element we had E1. So that is why I'm writing E1. Okay. Now um, now you see here we had I1. Here we have I0. Now here we have I2 dash because see I have referred I2 dash here, so I'm writing it as I2 dash. Now you see between V2 dash and V2 dash and E1 there is one drop of A square R2 plus J I2 dash A square X2. So this is what? A square X2, sorry, it has to be X2. A square x2, and this is what? A square r2. So that is why when you transfer this r2 and jx2, you multiply it by the turns ratio square. Okay, so that is why this turns ratio square comes. So that is how you refer it to the primary. Okay, so now let us see the questions quickly. After discussing all this, questions will be very easy. Okay, so this is all the most of the things which has to be discussed for this first week. I have discussed this, and people who have missed this discussion, you can see the recorded lecture. Okay, if you have missed some part of this discussion. Okay, now let us go to the questions quickly. So let us go to these questions. 1 minute. So here what we have for this question. um, 1 second. Hmm. Okay, now here the question is very simple. So the question is that here what we have is that a 12 kVA 60 hertz transformer is used in a 50 hertz power system. Under this situation, what is the maximum amount of kVA that this transformer can handle? Okay, now it is said that so phi max is the, so the phi max is this flux density. Now you know that this no load current I0 has two components, which is IC and I phi, and this I phi is what you say responsible for setting up this phi. Okay, so they are saying that the no load current is not changing, so indirectly they are saying that the phi is not changing. Okay, so they are saying that this I0 is not changing, so phi is not changing. Okay, So that is what they mean to say like this. So what will happen? So we know what is the EMF equation. EMF equation we have seen the RMS value of the EMF, right? So what is this RMS value? Root 2 pi f phi m into n, and root 2 pi f can be written as 4.445. Okay. So 4.44 f. So root 2 pi becomes 4.44. So I'm writing it as 4.44 pi max into frequency into n. Now in first case they are saying that 60 hertz was used. Now 60 hertz it's rated for 60 hertz. Okay, so E rated is what you say becomes what? 4.44 pi max into 60 into n. Okay, now what we are doing, we are now giving it as E, what you say, E operating. We are operating it at 50 hertz. So what will become? It will become 4.44 pi max into 50 into n. Okay, now so you can see that E operating becomes how much times? It becomes 5/6 times of E rated, because there is 60 here and there is 50 here. So if I take this ratio, you will get it as 5/6 of E rated. Okay, so what will be the kVA? So so it is saying that they have not told anything about the current. Okay, so they mean to say that the operating current is still the same. Okay, so what will happen? So your kVA rating is proportional to E operating into I operating. Now you see that they are saying that in this, basically they are not changed the current. Okay, current is still the same. They have not mentioned anything about the current, so it is still the same. Okay, so what it becomes? It becomes 5/6 times, 5/6. Okay, so 5/6 E rated into I operating. Okay, now we know that what is um, E rated into I operating. So it is 12 kVA. Okay, so this will become what? It will become 5/6 times of 12 kVA, which will give me what? It will give me 10 kVA. Okay, so the correct answer is 10 kVA. So if there is any doubt, please stop me in between. Okay. So if there are any doubts, please stop me. I hope this question is clear, right? Is there any doubt in this question? Okay, so I'll move to the next question. This question was very easy, because now you're basically what you're doing, you're operating a 60 hertz transformer at 50 hertz. So basically your E will change. So E, what will be the new E? It will be 5/6 times of the original E. And because you're not changing the operating current, so kVA rating will also become 5/6 times. So what is the kVA rating which is given in the question? It is given 12 kVA. So 5/6 of 12 kVA becomes 10 kVA. Okay. So this question is easy. You will see that the questions are not difficult. Okay. So now in this question, what they're asking you that what will be the value of phi max. They have said that the number of turns are 100, frequency is 50, RMS value is 110. They're asking you what is the phi max. Okay, and remember, this is the thing. Okay, milliweber, they will be giving you the units in the question. So these are the questions in which you enter the answer in the form of numerical answer questions. So you please check the units. Okay, here they're asking milliwebers. Okay, so you have to enter the answer in milliwebers. Okay, so we know what is the RMS value of induced EMF. We have derived it, right? So it is what? Root 2 pi f pi max into n. So it will become what? Root 2 pi, frequency they have given as 50 hertz. Okay, this is volt. So this is 50 pi max into 100. This E they have given as 110. Okay, so root 2 pi is 4.44 into 50 into pi max into 100. Okay, so if you calculate this, if you divide this 110 by this number, which is this 4.4415 to 100, so you will get it as 4.95 into 10 power minus 3 Webers. And because they have asked the answer in milliweber, okay, so you should not enter it as 0.00495, okay. Instead, you should enter 4.95 milliweber, okay. It is very important to check what is asked for the numerical question, okay. Is there any doubt in this question? This question was very simple, is it not? Just directly the application of formula. Is there any doubt in this question? So did you understand this question? Okay. So let us now go to the next question. Now in this next question, so this is the data which will be common for the upcoming four subsequent questions. Okay. So in this question, what is said? It is said that these two transformers are connected in cascade as shown like this. So this is the rating of the transformer. So this is what? This is 480 volt is to 1200 volt, and this is 1000 volt is to 400 volt. Okay, so this is the rating of the transformer, and they both have the same kVA rating. Okay, 5 kVA. Now they're asking what is the maximum value of Vs you should supply that it does not exceed the voltage ratings of any transformers. Okay, so someone asking something. What is someone asking? Okay. So is someone can you people other people can they mute themselves? Please mute yourself if unless you don't have doubt. Please mute yourself. Okay. Um. Okay then. I guess uh, I can. Ha. I'll mute Rajendra P. Okay. I think you are having some issues. I have muted everyone. Okay. So let us now go back. I hope there are no noise issues. Okay. Okay. So this is the case. Okay, now this is the voltage ratings. 480 volt is to 1200 volt and 1000 volt is to 400 volt. Now we have to supply Vs in such a way that any of these voltage ratings are not exceeded. Okay, so what we will do? So you can see that minimum of, so you see these two voltages. This voltage, suppose let us call it as E middle. Okay, so E middle, uh, it can be two values. It can be either 1200 volt or it can be 1000 volt, right? So what should be the value of E middle such that it does not exceed any of this 1200 volt or 1000 volt? See, because if we operate this E middle at what you say 1200 volt, suppose you give 480 volt here. So let us take case one. Okay. So this is the case one. So the case one is you gave 480 volt. So there are, so let us start with the 480 volt. So if you give 480 volt, so this is a 480 volt is to 1200 volt transformer. So on this side, it will become 1200 volt. Now this 1000 volt, see, you cannot give more than 1000 volt on across this transformer winding. So what will happen? This transformer will get damaged, right? So what should be the minimum value which you should give at this common E middle? You should give 1000 volt. Okay. So let us take case 2. So if you give 1000 volt here, so you should give the voltage in such a way here at this input Vs, okay, that it should not exceed this 1000 volt. So basically what is the maximum limit across this E middle? It is 1000 volt, right? So you cannot give more than 1000 volt at E middle. So this is 1000 volt. Now as per this voltage ratio, 480 volt is to 1200 volt. So what what will Vs become? So Vs will become 1000 into, okay, 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 first question. Okay, 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 first question. Okay, so let us go to this question. This this one, this one. Okay, this one. Okay, so this is the EMF. So basically, what they're asking you is, indirectly they have given you the number of turns. Number of turns is 100, frequency is 50 hertz, and RMS value is 110 volt. Is it not? Now, what they're asking, they're asking you to calculate phi max. Okay, what will be the phi max? Now, so how we can find this phi max? Okay, so if you go in the very beginning, we have derived this expression. Okay, so here what we did was we used Faraday's law. Okay, so as per the Faraday's law, what is the EMF induced? EMF induced is rate of change of the flux linkage. And what is flux linkage? It is number of turns into the flux phi. Okay, so this E1 will become what? E1 will become N d phi by dt. So what was the phi? So you see the phi which we have taken here is phi m sine omega t. Okay, because we wanted an AC value of flux, because for an EMF to induce, the flux has to be either time varying or space varying, because this is a transformer which is a static device, so it cannot be a space varying because there is no rotation in the transformer. So what it has to be? It has to be time varying flux. So what is a time varying flux? It is a AC flux. So let us suppose take phi s phi m sine omega t. You can also take phi s phi m cos omega t. It's not a problem. Okay, so for now let us take phi s phi m sine omega t. Okay, so what will E1 become? It will become N into d by dt of phi m sine omega t. So what is this derivation of? Because phi m is a constant peak, so phi m will come out, and there will be only derivation of d by dt of sine omega t. So what is the derivative of sine omega t? It is omega into cos omega t, right? Now you see, you can, what is the RMS value of an AC signal? Okay, so this is a AC signal which is A sine omega t. RMS value means what? Root means square value. So what we do, we square the, suppose A sine omega t is the function which is given to us. So first we square this. So square of A sine omega t is what? A square sine square omega t. Then we calculate the mean. So what is the mean? Mean is nothing but the average 1 by t integration of 0 to t a square sine square omega t, which will give us the average, which is the mean. So we have first done the square, then we have calculated the mean 1 by t of 0 to t a square sine square omega t, and then we have taken root, a root function. So if you do this, you can calculate this, you will see that the RMS value of a sinusoid signal will come out to be A by root 2. Okay, so that is why if we have a sinusoid signal like this, N phi m into 2 pi f, phi m means maximum value, phi m is the peak. Okay, phi m, this is the peak. So N into phi m into 2 pi f. So this is our, what you say, phi, this A. So what is the RMS value? It is A by root 2. So what it will, this will be? This will be root 2 pi f into phi m into n. So this is what the RMS value equation is. This you will find in all the textbooks. Okay, all the standard textbooks, you will find this EMF equation for the transformer like this. Even for the synchronous machine also, you will find the similar expression. Okay, we will discuss it in the subsequent classes. So this is what? Root 2 pi f phi m into n. So this is your E1, RMS value. So that RMS value expression only I have used here. Root 2 pi f phi max, phi m is phi max into n. Now here everything else was given to us. RMS value of EMF was, E was given as 110. This is root 2 pi, phi is 50, right? 50 hertz frequency, and then n is 100. This is phi max into 100. Now you will see root 2 into pi is 4.44. Okay, so this will come out to be 4.44, like that. Okay, so from all this I can find the value of phi max. So you will see that the value of phi max will come out to be, after, if you simplify this expression. Okay, because I do not have time for simplifying the like using the calculator in front of you. So but I have noted down the answers previously. Okay, so that is why if you can calculate, so you will get it as 4.95 milliwebers into 10, like 4.95 into 10 power minus 3 Weber. So it will come out to be 4.95 milliwebers. Is this question clear now? Uh, Okay, sure, no problem. Okay, so now let us go to this question which we were discussing. So we had to give a voltage Vs so that this what you say this road this transformer winding voltage ratings are not exceeded, right? So in the first case, what we did, we gave Vs as 480 volt. Okay, so if we give it as 480 volt, so this because of this turns ratio here for this first transformer 1. So this is transformer 1. So this will become what? 480 is to 1200. This will become 1200 volt on this side. But see, the transformer to the primary winding voltage rating is 1000 volt. So 1200 volt will exceed the 1000 volt, and hence this transformer will get damaged. Okay, so this case is not correct. So now we will go to the case 2. So what we will do, we will assume that okay, the maximum voltage at which this transformer winding can take is 1000 volt. Okay, so now we are going in this direction. So we are limiting this voltage to 1000 volt. So what will this voltage become on this side due to this what you say, this turns ratio? So this will become what? 1000 into if this is 1200 volt, we get 480 volt. So if we give 1200 volt, so this becomes 480 volt. So what will happen if you give what you say this as so if you give 1 volt, what this will become? This will become 480 by 1200. So if I give 1000 volt, so if I give 1000 volt, this will become 480 by 1200 into 1000. Is it not? So that is why Vs will become 480 by 1200 into 1000. So basically I'm multiplying this 1000 by the turns ratio. Okay, 1000 into 1 by A. Basically if this is A is to 1, so I am doing 1000 by A. Okay, so if I do that, you will find that this Vs will come out to be the what value it will come out. So I guess correct, it will come out to be 400. Very good. Okay, so this is 400. Okay, so if you give 400 volt here, so this as per the transformer ratio, this will be 1000 volt, and hence it will be within this 1000 volt limit. Okay, so that is why this voltage has to be 400 volt. Okay, now we will go to the next question, which is the what you say continuation of the same question system. So here they're asking, what is the maximum value of supply current that can be drawn without exceeding the ratings of any of the transformers? Okay, so what we need to do, we need to find the maximum value of current is. Okay, so that any of the transformer ratings are not exceeded. So let us now do, so this is a 5 kVA. Okay, so 5 kVA is the rating for the two transformers, and the voltage ratings are also given on the both sides. So let me hide this. Okay, so here what you have, I have this 1000 volt is to 400, and here I have 480 is to 1000. Now for a 5 kVA transformer, this current, let us suppose, is I2, this is I1. Okay, so what will be I2? I2 will be what? Because this is power. Now this is a single phase system. So for a single phase system, power is V into I. Okay, so this power basically is V, voltage into current. So if so voltage rating is given to me, power rating 5 kVA is given to me, I can find the current rating. So what are the current ratings? So current rating for this transformer is what? 5000 by 400, and here it is 5000 by 1000. So this is the current rating. So the current rating here is your 5 amps, and on that side it is 5 by 4 amps. Okay, so this is how it will come out to be. So this is, so this for this transformer it is 5 amp is to 5 by 4 amps. Okay, now for this transformer, what will be the current rating? So 5000 by 480 and 5000 by 1200. So this will be the current, because voltage into current is power, and power is given to us as 5000. So if I have to find current, so what will be the current? Current will be power by voltage. Okay, so that is what I have done for all the windings. Like this is 5000 by voltage 1000, 5000 by voltage 400, 5000 by voltage 480, 5000 by voltage 1200. So like that I can get the current ratings. Okay, now you see here, because again, like this previous case, here we have the two windings which are connected like this. Now, for this case, the current rating is, एक minute. Okay. So for this case, we have the current as 5 ampere, and for this case, so it is like this. Okay. Now, here we have 5 ampere rating for this transformer, and for this transformer winding the current rating will come out to be 5000 by 1200, which is 4.167 ampere. Okay, now you can understand very straightforward that if you have to operate at within any of the two currents, you should operate at the lesser current, right? Because that is common to both of them. So we will operate at 4.1667 ampere. Okay, so that the rating of this transformer current rating is not exceeded. Okay, so if I take this current as 4.1667 ampere, so on that side what it will become, you can just multiply the what you say ratio, so you will get the current as like this. Okay, so this will become 4.1667 into 1200 by 480. Okay, so this will come out to be 10.416 ampere. So why we took 4.1667 instead of 5 ampere here? Because we have to take minimum of the two. Okay, we have to take minimum of the two. So if we take 5 ampere, so what will happen is that this transformer winding current rating will exceed. Okay, so that is why we have to take 4.1667 ampere, so that this transformer rating is not exceeded. Okay, so if we take 4.1667 ampere, so we can get the current is here as per the voltage, as per the turns ratio. Okay, so you can multiply the ratio accordingly, because this will become what, 480 into is should be equal to 1200 into 4.1667 ampere, which we have seen. Okay, for an ideal transformer we have seen as per the mmf balance we get like this. So is will become what, 1200 into 4.1667 by 480, which you will get as 10.416 ampere. Okay, is there any doubt in this question? Okay, so this is basically, I'll tell you. So volt ampere is your apparent power. Okay, so we will discuss this. Okay, so this is denoted as S. Okay, now S has two components, real power and the reactive power. Okay, so this P is real power and Q means the reactive power. Okay, so when I meant V into I meant to say it as S, which is the apparent power whose unit is volt amperes. Okay, एक minute. So that is volt amperes. Okay, now P, which is the real power, so you can see it is a power triangle. Okay, that is what I said. For understanding electrical machines, it is important to have the circuit theory good. Okay, then only you can understand all these terminologies. Okay, so this is a power triangle. Okay, now this is a phi. Now you see this is your apparent power whose unit is in volt ampere. This is the real power whose unit is in watts, and this is the reactive power whose unit is in var, which is VAR. It is written as VAR. Okay, now you see as per the this power triangle, so if I apply this, so this cos phi is called as your power factor. Okay, which is P by S. So what is your real power? real power is S cos phi. So it means what? This S, basically this total VI, voltage into current, if you do like this, so this V into I will have two components. One is the reactive power only and one is the real part only. Okay. So so this real part VI cos phi. Okay, this will become as VI cos phi, and your reactive power will come as VI sin phi. But the overall, which is the, you see the if you see only the magnitude, this is V into I. Okay, V into I. So this V into I is basically, I meant to say it as here. Okay, this is what I meant to say, not the real part. Okay. um, so, do you want me to discuss this in detail? Because it will take. Okay, okay. So, if needed, I'll start with little bit of this in the next class. Okay. Okay. I'll start with a little bit of these things in the next class. Okay. I understand that, but we are actually a bit short on the time. This is a very huge topic, na? So that is why I'll discuss this. Okay. I'll discuss this. Okay. Okay. Okay, like this. So that is what I meant to say. Okay, this apparent power. So here basically voltage into current is this apparent power, 5000 kVA. Okay, that is why it is written as VA, not watt, kilowatt. It is not written as kilowatt. Okay, because see, in the transformer you have what you say, this, you have this resistance part and you also have the reactance part, right? So what will happen is, you see, if I have only the resistance, so what will happen? This voltage and current are like this. V by I is equal to R. Okay. But if I have uh, like this, if I give a voltage across this R and L, so what will happen? So this will V by I, which is basically this I. So I will become what? V by R plus JXL. Now you can see that this is a complex number, right? So that is why it will also have the power which is associated with this V into I will be this V square by R plus JXL. So this is a complex power. Okay. So that is why, to represent this complex power, we have this volt into amps, which tells us that if so this will have both the real part of the power of the component, and also it will have the reactive part of the power. Okay. So that is why we represent it like P plus JQ. Okay, I'll discuss this a little bit more in the next class. Okay. Now okay. Now we will go to this question. So here what is asked is, now again in this part of this question, they're asking us what will be the maximum value of the kVA that can be transmitted to the load without exceeding the ratings of any of the transformer. So without exceeding the voltage rating, without exceeding the current rating. So we have seen from the first question that what is the maximum value of Vs at which we can operate. So in this first question, we got that Vs as 400 volt. Okay, so that is the maximum value of voltage at which we can operate without exceeding the voltage ratings of any of the windings. Similarly, here also we have seen what should be the maximum value of current at which we can operate, Is, so that we do not exceed any of the current ratings. Okay, this is 10.416. So what will be the maximum kVA? So maximum kVA will be Vs into Is, simply Vs into Is. So we have seen the safe value of Vs, and also we have seen the safe value of Is. So this we have seen in the question number, this is what? This is question number 3, from question number 3, and this we have gotten from question number 4. So what is the safe value of Vs? It was 400. And what is the safe value of Is? This was 10.416 ampere. Okay. So this is 10.416 ampere. So if we take the product of this, we can get the maximum value of PA which we can operate without violating any ratings. Okay, so you will see that it will come out to be what? It will come out to be 4 point. Basically, if I do this, and it is asking the answer in what? It is asking the answer in kVA. Okay, this is very important. So if I do this, this will 400 into 10.416. So this will come out to be 4166.67 VA, and if I write it in kVA, it will come out to be 4.1667 kVA. Okay, so this is the question. Now we will go to the next question, which is again the continuation of the same problem. Now here they're asking us what is the estimate the value of RL so that we do not exceed again any ratings of this transformer. Okay, so we should not exceed any of the ratings of this transformer. So we can do it in two ways. Okay, so the one way is, so the first method is that I can so first of all, we know that what will be the value of the resistance which we can get from this safe Vs and safe Is, right? So Rs, which is this safe Vs by safe Is, so that no voltage or current ratings are exceeded, we can get on this side of the of the winding. So what is that safe Vs? Safe Vs is 400 by 10.4167 amps. Okay, so this is the value of RS, but this is RL is here. So what we will do, we will transform this RL first here, and then again we will transfer this RL on this side of the winding. Okay, so we know how to transfer the resistance or inductance of the what you say, right? We have transferred it also previously. Here also we have transferred it. So how we transfer it? We multiply it by a square. Okay, you can see this explanation here. So for transferring this R2 JX2 on this side, I had multiplied it by a square. Okay, so let us multiply it by a square. So what is A? A is N1 by N2. So A is what? So here in this case, so for this case, so let us write it as A1. This is as A2. So A1 for the first case is 480 by 1200, because this is equal to V1 by V2, which is also equal to N1 by this N2. Now A2 is what? A2 is 1000 by 400, which is suppose V2 by V3, and this is N2 by N3. Okay, now here this is N1 is to N2, and this is N2 is to N3. Okay, let us say like this. So it is like this. Okay, so these are the ratios. So how we can transfer this RL? So if I transfer this RL here, so this will come out to be, so on this side, suppose RL dash, so RL dash will come out to be A2 square RL. Right, you can see this in that previous discussion. Now again, if I transfer this RL dash to here, which is RL double dash, now RL double dash will be what? A1 square RL dash. Now A1 square RL dash is what? A1 square A2 square RL. Okay, so this A1 square A2 square RL double dash should be equal to RS. Okay, so this RS becomes A1 square A2 square RL. Okay, so this RS is 400 by 10.416, which is equal to A1 square. So 480 by 1200 square into A2 square. So A2 is 1000 by 400 square RL. So we can, from this equation here, we can find the value of RL. And one very simple way of finding this RL is, I'll tell you. Okay, so here, you know, so what is the safe value of voltage in the middle? So the safe value of the voltage in the middle was 1000 volt. So if I take 1000 volt, so because if I give 1000 volt on this, so I'll get 400 volt here. So basically I'll get 400 volt, which is the basically V safe on this side. Okay, so V safe across RL is 400 volt. Okay, so V safe on this side, V safe this one RL is basically 400 volt. Okay, and what about the safe current? So Is we have seen. So here, if I give 4.1667 amperes, so on this side, from this turns ratio, this current ISRL will come out to be like this. Okay, so I safe RL will become 4.1667, and then I'll have to do like this. Okay, 4.1667 into A2. Okay, so this will come out to be 1000 by 400. So this will be, so this RL value will be what? V safe RL by I safe RL. So basically what I did, I whatever VS and IS I had, I just got the VS and safe VS and safe IS required across RL on this winding. So either you can transfer the RL on this side, or you can transfer the value of V safe and I safe on this side. Is this question clear? To get the value of RL. Okay, so let me just see. This is 4.1667 here. And here what I have 1000 is to 400. Now, if I have to find this IRL safe, right? Now, let us do this MMF balance. So, Hana? Yes. Okay. Okay. So, if you do MMF balance, then you'll get like that. Okay. You'll get this only. Okay. Now, let us go to the next question. Now, this in the next question, what we have to do, we have to find the RMS value of the primary current I1, and everything else is given to us. Okay, so how we will do it? So let us see this question. So in this question, we have Vs, we have Jx. Now what I'll do, I'll transfer this RL on this primary side. I'll refer it to the primary side. Okay, and we know how to refer it also, right? So this is what? This is N1 is to N2 is what? A is to 1. So A is N1 by N2. So when I transfer this RL, so this will become RL into A square. This is nothing but RL into N1 by N2 whole square. Okay, so what is the value of this X, which is Vs is given as 250 volt. Jx is given as X is given as 12, so this is J12. And if I transfer this RL on this side, so this will become N1 by N2. So this is 600 by 150 whole square. So this becomes 4 square. So this is 16 ohm. Okay, so this is 16 ohm. So basically what we have is, we have a circuit like this. We have 250 volt, we have uh, basically your J12, and here when I have referred this, so this is what? This is RL dash is 16 ohm. Okay, so what they're asking? They're asking us to find I1. So what is I1? I1 is 250 by 16 plus J12. Is it not? But they are asking us to find the what you say RMS value. Okay, so if I do this if I write this 16 plus J12 in the this is rectangular form, right? 16 plus J12. So rectangular coordinate form. If I write this in polar form, so what this will become? This will become root over of 16 square per 12 square angle of tan inverse 12 by 16. Okay, so I'll write like this: 16 square plus 12 square angle of tan inverse 12 by 16. Okay, now we are only represented what interested in this the RMS value. So RMS value of this current I1 RMS is nothing but magnitude of this. Okay, so the magnitude part will come out to be 250 by root over of 16 square plus 12 square. Okay, so if I do this, so 4 square plus, okay, so I can take out the 4 part, and this will be what? 4 square plus 3 square. If you do 4 square plus 3 square, you will find that this will come out as 5. Okay, so this is what? 250 by 20. So 250 by 20 is how much? 250 by 20. Okay, so 250 by 20, you will get it as 12.5. Okay, this will be 12.5 amperes. So RMS value. Okay, see, we know that in a polar format, this represents the RMS value, right? For a voltage also, I can write it as 250 angle 0. So this 250 part represents the RMS value, and this 0 represents the phase angle. Okay, so because we are only interested in knowing the RMS value of the current, so that is why I only focused on the magnitude part. Is it clear? Okay, now let us go to the next question. Now in the next question, we have to find the RMS value of the secondary current. Very simple. We know the RMS value here of the I1. So I1 RMS value we have found from the previous question is 12.5 ampere. Now what will be the RMS value I2? We can just use, you know what we can use? We can use just the MMF balance. So N1 I1, N2 I2, N1 is what? 600 is to 12 into 12.5, and 2 is 150 into I2. So if we do that, we can get the I2. So this I2 you will find will come out as this 4. So 12.5 into 4 is 50 amps. Okay. So this is how you will do this. Now we go to the again the next question. Now in this next question, what we have to do? Now you see the person who asked me the doubt regarding the VA and watts. Okay. So they are here, they're asking estimate the power in watts. Okay. So they are asking you to find the real power supplied by the source. Okay. So as I said, so what is this? So Vs is angle 0. So this is 250 angle 0. And I1 we have tried to find the current, right? So what was the current which we have found in the full expression of the current? So here you see this is 250 by root over of 16 square plus 12 square and this angle, right? So this angle gives us the phase angle. Okay. So let us now write it like this. So this is 250 by root over of 16 square plus 12 square, and this is angle tan inverse 12 by 16. Okay, so this becomes what? This we got as 12.5 angle of minus, because this is on denominator. So if I send it in the numerator from the complex number operations, we get it as minus tan inverse 12 by 16. Okay, so this is the current I1. Now this is what? So we have Vs angle 0 and I1 angle 0. Now what is the expression of the power S? So you will see the power expression of power is Vs into Is or I1 conjugate. Okay. So if I take conjugate, so what will happen? So conjugate of I1, this minus will go, because in the conjugate if we take off in this polar format, so negative angle will become positive or the positive angle will become negative. Okay. So this will become what? 250 angle 0 into 12.5 angle tan inverse 12 by 16. Okay, so this is S. Now what is the what is the watt thing? So P is real part of S. Okay, so we have seen that this comes out to be VI cos phi directly, where this V is VRMS, I is RMS, and this phi is the phi angle. Okay, and if you do this, like if you write this complex form, like so if I write the real and imaginary part of this, so this you can see from here also. So this is 250 angle into 12.5. Now what is this? So it has to be cos, this is cos plus, we write like this, right? So if I convert the polar into coordinate what you say coordinate geometry, so this will become what? 250 into 12.5, this is the magnitude, and this is what? Cos phi plus j sin phi. And what is phi? Cos of phi is tan inverse 12 by 16. Okay, plus j sine tan inverse 12 by 16. Okay, so this is what? So this is nothing but VI cos phi directly. So the real part is what? 250 into 12.5 into cosine of the angle of tan inverse 12 by 16. So that is why when I in that question when I wrote it like this, right? VI cos phi, that is how I wrote it. Okay, is your doubt clear right now? That person who asked it? Okay, so this is how you do it. So you will get VI cos phi. So if you can find it. Okay, so you have 250 to 12.5, and you can do the tan inverse of 12 by 16. You will get some angle. Take the cosine of that and multiply by this. You will get the power supplied in watts. And one very simple way to find the power is that you will find when if I do this now. So from the power triangle basically gives the relation like this. It also gives the relation like this: Z R X. Okay, this phi is same in both the triangles. So what will happen if I multiply I square here, I square here, I square here? This triangle will become this triangle. Okay, so if I have to find this P, so P can be VI cos phi, and in the case when you have this R plus JXL kind of load, so if you have R plus JXL kind of load like this, okay, so in this case your real power will become I, you directly become I square RL. Okay, so maybe I'll discuss this relation in the next class. Then your life will become very simple. Okay, you did not need to do like this. You can if you know this RMS current I, so 12.5 square into R. Now this R either, so because I have taken this I here on this IS, either I can take I2 square RL, okay, or I should take this IS square into RL dash. RL is referred in this side, okay, so RL dash, or I2 square RL. So I2 square is what? I2 is basically I2 on this side we have found it as 50 square. So it is either 50 square into 1, or it is 12.5 square into RL dash. So RL dash we have found it as 16. So you will see that both of these will give you 2500 watts. This will also give you 2500 watts. Okay. So this is a very interesting thing. I'll maybe discuss this again in the next class. Okay. This is very interesting. Okay. Now let us. This question is clear. Even if this part is clear, now that is also enough. Okay. This part maybe I'll explain in the next class. Okay. Now let us go to this data. So for this data, what we have is that we have this current 8 ampere flowing here. It is having 100 turns. We have I2 current flowing here. It is having 125 turns and 100 ohms. And this is having I3 current flowing here, which is having 50 ohms and 50 turns. Okay. Now what we have to do, we have to find the RMS value of the current I2. Okay. Now you have to be very cautious. Now you can just not directly do it like I2 is equal to what? You should not do it like, okay, N1 I1 plus is equal to N2 I2. No, this will be wrong, because there are three windings in this transformer. So when you do the MMF balance, you will get it like this. Okay. Okay. This is the correct MMF balance of a three winding transformer. Okay. So you should not do such a mistake here. Please do not make this mistake here. Okay. So you should write the correct MMF balance equation. Okay. So you will get it as N1 I1, because this current is entering here and these two currents are going out. So you will see that this I2 and I3 will come with a minus sign. Okay. So this will become N2 I2 plus N3 I3. So this is your one equation. Now here you have N1 and I1 value. So this is 8 into 100 is equal to N2. N2 is what? 125 into I2 plus N3 is 50 into I3. So this is your equation 1. Because there are two unknowns I2 and I3, we need another equation. So what is that another equation? So in this case, we have V1 is to V2 is to V3 is equal to N1 is to N2 is to N3. Okay. Now what is this V2? So what is this V2 voltage? So this voltage V2 is nothing but I2 into 100. And what is this V3? V3 is I3 into 50. Okay. So basically V2 is to V3 is N2 is to N3. Is it not? So V2 by V3, which is I2 into 100, because from Ohm's law we know voltage is what? Current into resistance. So we have V2 is equal to I2 into 100 and V3 is equal to I3 into 50. This is equal to N2 by N3. Okay. Now N2 by N3 we know. So what is the value of N2 by N3? So N2 by N3 is 125 to 50. Okay. So this is our second equation. So you have basically first equation and second equation, and you have two unknowns I2 and I3. So you can solve for it. Okay. So if you solve it, you can just solve it. You will get I2 as 4.84 ampere. Okay. Is this question clear? Okay. So this is how you can find it. So you have two equations, and remember the MMF balance for this three winding transformer will not be N1 plus N1 I1 plus N2 I2, because you have now three fluxes, right? So there will be flux due to the primary winding, then there will be flux due to the secondary winding, flux due to tertiary winding. So if I do that, 5 primary plus 5 secondary plus 5 tertiary equal to 0, and then I apply MMF balance. Okay. then you will see that this is how it will come like that. Okay, this will not be n1 equals to n1 I1 equals to n2 I2. No, it's not in a case. In this is only valid for two winding transformer case. Okay, now let us go to the next question. Now, in this next question, we have to calculate the RMS value of I3. We can just, again, because we have already solved for I2, so you can substitute in any of these two equations and you can get I3 value. Okay. This is not nothing but just you get I2, then also you get I3. Okay. Because you have two equations. So if you do it, you can solve for both the variables I2 and I3, right? So you will get the I3 also. So I3 you will get as 387.87 ampere. This you can just try. Okay. Oh, I thought someone came. Okay. Now we go to the this question. Now here what we need to do, we need to find the supply voltage. Okay. Now what is the supply primary voltage? So it we have seen that, right? So what we have seen, that we have seen that V1 is to V2 is to V3. So V2 is I2 R2, ठीक है, और V3 is I3 R3. So V1 by V2 is N1 by N2, or V1 by V3 is N1 by N3. Now we know what is V2. It is I2 R2. So we can get V1. V1 is what? N1 by N2 into I2 R2. Similarly, from this also you can get the value of V1. N3 by N1 by N3 into V3 is I3 R3. So you will see that V1 will come out to be same in both the cases. Okay. Is this clear? Okay, so let me go to the this question. So here what we have to do is we have to calculate the power. Maybe what we can do is we are left with only two questions more. We can discuss these two questions in the next class. Or do you want me to discuss this question so that it will be easy to solve the assignment? Any of that is okay with me. Maybe I can discuss it so that you can what you say, see the recording and maybe solve for the assignments if there are similar questions. Okay. Now what we need to do, we need to find the total power delivered. Okay. So the total power delivered is what? So the total power delivered is nothing but your this voltage V1 into I1. So this V1 into 8 we can do, so we can get the total power. But total power, as you can see, you will get as S, but it is asking watts. Okay. So what will be the power in watts? So you can just see that the power in watts will be nothing but equal to I2 square R2 plus R3 square R3. So in if you do like this, you will get the power in watts. Okay, we have seen earlier from this power triangle also that if you do like this, you will get the same value. Okay, like Vi cos phi will be same as I square into R. Okay, but because there are two R's, different R's in the separate windings, so if you do the I2 square, I square into R here for this winding plus I square into R for this winding, you can get the total power. Okay, in watts, because this is the real power. Okay, so if you do this, you can get the value of total power which is delivered by the source. I will, for solving the assignment questions, you can follow this. I will explain this. I will again, what is discuss this explanation in the next class. Okay, that how this exactly comes. But for solving this, you just know how this is how you can do it. Okay. Now the impedance seen by the source. So what will be the impedance seen by the source? You can just transfer these impedances, right? So either you can transfer the impedances or you can just do voltage by this current. Okay, so you can do either way. So if you do voltage by current, you will get the what you say impedance seen. So 8 ampere is the what you say this current, and voltage we have we have found from this expression, right? So if you do it, so in the in that question you will get the voltage to be as 387.87 volts. Okay, so this is the voltage which you would have seen. Okay, now if you do it, so this is not 387%, this is something else. Okay, I just wrote the other answer there. Now, so this is the voltage. So this Z will be 387.87 by this current 8. So if you do this, you will get the impedance seen by the source. Okay. So that is all for this class. I'll explain these things again, some of the things again, which I did not get the time to properly discuss. So that is it. Okay, for this class. If you do not have any doubts, you can leave. If you have any doubts, I can discuss it now. Okay, I can clear those doubts. So is it okay, this class? Is there any doubt? So if there is no doubt, then you can leave. Okay. Okay, so what will happen is these NPTEL people, they will share with you they would have shared with you some what you say, Google spreadsheet. Okay, so in that spreadsheet there will be a YouTube recording for my in the YouTube video they will find the video recording of my class as well as video recording of the other TA. Okay, it will be mentioned. Also these things which I have discussed right now, no, I will upload that this document also. Okay, these all notes. So I will share. So I'll share the notes and the video, and these NPTEL people will share you the Google spreadsheet on which these things are available. Okay, Sukriti? Okay then. So that is it. So you may leave the class. Okay. So okay then. Okay then. Okay then. Okay. Okay. Sure. Okay then leave. Okay. I'm okay. Sure. Okay then. Thank you. I'm also leaving. If there is no doubt, we will again meet in the next class. Okay. Okay. Sure. Sure. Okay then. Okay then. I'm also leaving.